Hey guys, welcome to another episode of the Human AI podcast. Today we're going to talk about micronutrients. We're also going to talk about salt, water, and how it's transported and how it's controlled in the body. If you don't know the format of this podcast, I talk to Grok, an AI, and Grog is the teacher. It explains to us these concepts, and I ask questions as the student. I'm not clever to understand these things. You're probably better than me. Having said that, let's get into today's topic and make sure to cross reference everything you hear from Grok. Okay, Grok, let's kick things off with micronutrients.
All right. Welcome back to the Human AI podcast. Micronutrients are vitamins and minerals needed in small amounts for body functions like growth, immunity, and energy. Unlike macronutrients, carbs, fats, proteins, they don't provide calories, but are crucial for enzymes, hormones, and cell health. Examples: vitamin C, immune support; iron, oxygen transport; zinc, wound healing; salt, sodium chloride, and water are key for fluid balance, nerve signaling, and muscle function. Want me to start with specific micronutrients or dive into salt and water transport first?
I want to understand what you mean that they don't have calories. I don't understand how this is possible.
Micronutrients, like vitamins and minerals, don't have calories because they aren't broken down for energy like carbs, fats, or proteins. They act as helpers supporting chemical reactions, e.g., vitamin B for metabolism, or building structures, e.g., calcium for bones, but don't provide fuel. Calories come from macronutrients supplying energy: 4 calories per gram for carbs, proteins; 9 calories per gram for fats. Micronutrients are used in tiny amounts, no energy release. Clear?
So for
Want an ex-
something to have calories, we have to have energy release.
Exactly. Calories measure energy released when the body breaks down food. Macronutrients, carbs, proteins, fats, get metabolized, releasing energy, calories, for fuel. Micronutrients, vitamins, minerals, don't break down for energy. They enable reactions or build tissues without releasing energy, so no calories.
I see.
Clear?
Okay, let's talk about nutrient bioavailability.
Nutrient bioavailability is how much of a nutrient your body absorbs and uses from food or supplements. It varies by nutrient, food form, and body conditions. Example: iron from meat, hemi-iron, is 20-30% bioavailable. From plants, non-heme, 5 to 15%, boosted by vitamin C. Factors like cooking, gut health, or inhibitors, e.g., phytates in grains, affect it. Micronutrients like fat-soluble vitamins A, D, E, K need dietary fat for better absorption. Clear? Want specifics on a nutrient?
I don't get it.
All right, simpler. Bioavailability is how much of a nutrient your body actually grabs and uses from what you eat. Some nutrients, like iron from steak, are easier to absorb, high bioavailability, than from spinach, lower. Things like cooking, other foods, vitamin C helps iron, or gut issues change how much you absorb. Clear? Want an example with a micronutrient?
Okay, but okay, what factors in the availability then?
Factors affecting nutrient bioavailability: 1. Food source: hemi-iron, meat, absorbs better than non-heme, plants. 2. Nutrient form: Cooked carrots boost beta carotene availability versus raw. 3. Diet interactions. Vitamin C enhances iron absorption. Phytates, grains block it. 4. Body status. Iron deficiency increases absorption. Healthy gut absorbs better. 5. Fat presence. Fat soluble vitamins A, D, E, K need dietary fat. 6. Processing. Milling grains lowers nutrient content. These impact how much micronutrient your body uses. Clear? Want one factor explored?
I don't get it.
No stress. Let's try again. Bioavailability is how much of a nutrient, like iron or vitamin C, your body can actually use from food. It depends on what you eat. Meat iron absorbs better than spinach iron. Cooking, boiled veggies release more nutrients. Other foods, eating oranges with spinach helps iron stick. Your body, if you're low on a nutrient, you absorb more. Gut health, sick gut, less absorption. Like, not all food nutrients make it to your system.
I don't
Clear?
understand how this is possible.
All right. Think of bioavailability like getting cash from a piggy bank. You eat a nutrient, money in the bank, but you can't use it all. Some coins, nutrients, are stuck. Why? Food type, meats coins pour out easy. Spinaches are glued. Cooking, heat loosens coins. Other foods, oranges pry coins free for spinach. Your
So you
body,
can poop nutrients then.
yeah, exactly. If a nutrient's bioavailability is low, your body doesn't absorb it, and it passes through, ending up in your poop. For example, only 5 to 15% of plant iron gets absorbed. The rest gets flushed out.
Why?
Same with
Is it too tightly bound?
Yep, sometimes nutrients are too tightly bound, like iron in plants, non-heme, locked in complexes by phytates or fiber, so your gut can't grab much, and it passes out as waste. Other reasons, poor gut absorption, e.g., damaged gut lining, inhibitors, like calcium blocking zinc, or excess nutrient intake. Body only takes what it needs. Low bioavailability means more gets pooped out.
I see. Interesting. So, what are the main sides of micronutrient absorption?
Main sites of micronutrient absorption. Small intestine. Primary site for most micronutrients. Vitamins A, B, C, D, E, K. Minerals like iron, calcium, zinc. Large surface area. Villi, microvilli, maximizes uptake. Stomach absorption. Some absorption, e.g., small amounts of B12 bind to intrinsic factor here. Large intestine, minor role. Absorbs some vitamins, e.g., K, biotin from gut bacteria. Small intestine's pH, enzymes, and bile for fat-soluble vitamins drive efficient absorption. Clear? Want details on one site or nutrient?
Tell us about the vitamins now. Tell us about all the vitamins. Well, yeah.
All right, let's cover vitamins quick. Vitamins are micronutrients, split into fat soluble, A, D, E, K, and water soluble, B complex, C. Here's the rundown. Vitamin A, eyesight, immunity, skin, and carrots, liver. Absorbed with fat and small intestine. Vitamin D, bone health, calcium absorption. From sun, fish. Small intestine, fat dependent. Vitamin E, antioxidant, cell protection. In nuts, seeds. Small intestine needs fat. Vitamin K, blood clotting, bone health. In greens, gut bacteria. Small intestine, fat based. B vitamins, B1, B2, B3, B5, B6, B7, B9, B12, energy, DNA, red blood cells, in grains, meat, eggs. Absorbed in small intestine, B12 needs stomach's intrinsic factor. Vitamin C, immunity, collagen, antioxidant, in citrus, peppers. Small intestine, water soluble. Fat soluble vitamins store in tissues. Water soluble ones flush out if excess, need regular intake. Bioavailability varies, e.g., cooking boosts C, fat boosts A. Clear?
Yes.
Want focus on one
Perfect,
vitamin?
perfect. Yeah, let's talk a bit about vitamin C. So, it's mainly absorbed where? In the buccal mucosa, stomach, and small intestine? And why? And what is buccal mucosa anyway? And tell us about the mechanism of absorption too.
Vitamin C, ascorbic acid, is mainly absorbed in the small intestine, with minor uptake in the stomach. Buccal mucosa, inner cheek lining, plays a tiny role, mostly in supplements like chewables, but it's negligible due to low surface area. Why small intestine? It has a massive surface area, villi, microvilli, ideal pH, neutral, and specific transporters. Mechanism: vitamin C uses sodium dependent vitamin C transporters, SVCT1, SVCT2, in the small intestine to move ascorbic acid into cells actively, driven by sodium gradient. Some passive diffusion occurs at high doses. Stomach absorbs less due to acidic pH and fewer transporters. Bioavailability 90% at low doses, under 200 milligrams. Excess, over 1,000 milligrams, gets excreted, lowering absorption. Clear? Want more on vitamin C's role or issues?
Yeah, what does it do, vitamin C anyway? And talk to us more about the mechanism of absorption. What does scurvy mean? And regarding the mechanism, so we have passive diffusion. And is it rapid? Is it slow? Is it carrier mediated transport?
Vitamin C as ascorbic acid does boosts immunity, white blood cell function, builds collagen for skin, bones, vessels, acts as an antioxidant, fights cell damage, and aids iron absorption. Scurvy, vitamin C deficiency causing weak collagen, leading to bleeding gums, bruises, fatigue, and slow healing. Historically linked to sailors. Mechanism of absorption: primary, carrier mediated, active transport via SVCT1, SVCT2 transporters in small intestine. Sodium driven, energy dependent, fast at low moderate doses, 30 to 200 milligrams, maxing at 90% bioavailability. Secondary, passive diffusion at high doses, over 1,000 milligrams, slower, less efficient, as transporters saturate and excess is excreted. Small intestine dominates due to large surface area, neutral pH. Stomach, minor. Buccal mucosa, negligible. Absorption rate slows at high doses due to saturation. Clear? Want more on scurvy or transporter details?
I do want more because I didn't understand it, to be honest.
No problem. Let's simplify. Vitamin C helps immunity, makes collagen, keeps skin, bones strong, protects cells as an antioxidant, boosts iron uptake. Scurvy, low vitamin C causes weak collagen, leading to bleeding gums, bruises, slow healing. Absorption happens mostly in small intestine. Main way, special proteins, SVCT1, SVCT2, grab vitamin C with sodium, pulling it into cells fast when you eat normal amounts, like an orange, 70 milligrams. Backup, at high doses like 2,000 milligram pills, those proteins get full, so some vitamin C slips through by diffusion, but it's slower, and extra gets peed out. Small intestine wins for its huge surface and right pH. Stomach and cheeks, buccal mucosa, barely help. Clear?
Tell me one
Want an
last time. Tell
analogy
me
or
one
more
more.
on scurvy?
Tell me one more time. Huh?
All right, one more shot. Super clear. Vitamin C boosts immunity, builds collagen for skin, bones, fights cell damage, helps iron absorption. Scurvy, no vitamin C, collagen weakens, causes bleeding gums, bruises, fatigue. Absorption, mostly small intestine. Fast way, proteins, SVCT1, SVCT2, pull vitamin C in with sodium, super efficient for normal doses, 50 to 200 milligrams, like in fruit. Slow way, high doses, 1000 plus milligrams, overwhelm proteins, so some vitamin C sneaks through by diffusion, but lots gets wasted in pee. Small
Okay,
intestine's
let
huge
me
area
let
and
me ask
pH
you
make it
about
king. Stomach,
yeah, let me ask you a bit about selected B vitamins. So specifically, I want to focus on the mechanism of absorption, and I want to understand Wernicke-Korsakoff syndrome, also, and pernicious anemia, intrinsic factors, haptocorin.
all right, let's dive into selected B vitamins, focusing on B1, B12 for Wernicke-Korsakoff and pernicious anemia, their absorption mechanisms and related conditions. B1, thiamine. Function, energy metabolism, nerve function. Absorption, small intestine, carrier-mediated, thiamine transporters, TPP1, TPP2, at low doses, 1 to 5 milligrams, active, sodium-dependent, passive diffusion at high doses. Deficiency, Wernicke-Korsakoff syndrome, linked to alcoholism or malnutrition. Wernicke's, confusion, eye movement issues, ataxia. Korsakoff's, memory loss, confabulation. Brain lacks thiamine for glucose metabolism. B12, cobalamin. Function, red blood cell formation, DNA synthesis, nerve health. Absorption, complex, stomach, and small intestine. In stomach, B12 binds to haptocorin, R protein, and saliva, protecting it from acid. In small intestine, pancreatic enzymes free B12. It binds to intrinsic factor from stomach parietal cells. Intrinsic factor B12 complex is absorbed in ileum via cubulin receptors, carrier mediated. Deficiency, pernicious anemia, from low intrinsic factor, e.g., autoimmune gastritis or poor B12 intake, vegans. Causes megaloblastic anemia, large, faulty red cells, nerve damage, fatigue. Haptocorin protects B12 in stomach, not for absorption, just delivery to small intestine. Bioavailability, B high, 70-90% at low doses, B12 low, 1-2% without intrinsic factor. Clear? Want more on one condition or absorption
This
details?
is good. Going to another topic, let's talk a bit about water and electrolyte transport in the GI tract too. Well, so digestive processes depend on these metabolic processes. Um, Explain this a bit, and then let's go a bit deeper into electrolytes. Yes, and their diffusion down electrochemical gradients, if you could explain that.
All right, let's cover water and electrolyte transport in the GI tract, tying it to digestion and electrochemical gradients. Water transport. GI tract absorbs 9 liters water daily, 2 liters from diet, 7 liters from secretions like saliva, gastric juice. Small intestine absorbs most via osmosis, driven by electrochemical gradients, sodium, chloride. Colon absorbs residual water, making stool solid. Digestion depends on water to dissolve nutrients, enzymes for breakdown, and electrolytes for transport. Electrolyte transport. Sodium, Na+, absorbed in small intestine, colon, via active transport, sodium potassium ATPase pumps, and co-transporters, e.g., NAF glucose, creates osmotic gradient, pulling water in. Nerve column. Chloride, CLA, follows Na plus via co-transporters or channels, maintaining charge balance. Potassium, K plus, absorbed passively in small intestine, actively in colon. Bicardiae, HCO3 minus, secreted in duodenum to neutralize acid, absorbed later. Electrochemical gradients. Dual gradients drive transport. 1. Concentration gradient, high Na plus outside cells, low inside, pushes NAFI into enterocytes. 2. Electrical gradient. Inside of cell is negative, due to ATPase, pulls positive ions, Na plus K plus in. Double electrochemical gradient. NAFIK plus ATPase maintains low intracellular Na plus, high K plus. This
Okay,
powers.
okay. Okay, let's talk a bit about osmolarity and semi-permeable membranes too, and how an increase in osmolarity means hypertonic environment.
Osmolarity measures solute concentration, MOSM osmol, in a solution, like body fluids. Semi-permeable membranes, e.g., cell membranes, gut lining, let water pass but restrict some solutes, like Na plus CLA. High osmolarity, more solutes, e.g., NaFi, creates a hypertonic environment, pulling water across the membrane toward the higher solute side via osmosis to balance concentrations. In GI tract, small intestine absorbs Na+, raising lumen osmolarity, making it hypertonic. Water follows from blood to lumen, or vice versa. Example, high Na+ in lumen, post-meal, pulls water in, aiding nutrient absorption. Low osmolarity, hypotonic, pushes water out, risking dehydration. Electrochemical gradients NAFIK plus pumps maintain osmolarity for water electrolyte transport. Clear? Want more on GI examples or tonicity effects?
That makes sense. Okay, let's talk a bit about passive transport and why that means down a concentration gradient. I don't know what the concentration gradient is. I've been learning this phrase years. I don't fucking know what it means. Does it mean like does it mean I have a y equals minus 2x graph and the ball is running down? Because that's what I'm visualizing.
Haha, love the visuals. Let's clear it up. A concentration gradient is the difference in how much of a substance, like Na plus or water, is in one area versus another. Imagine a crowded party, high concentration on one side of a room, and an empty corner, low concentration. People, molecules, naturally spread to the empty spot. Passive transport means molecules move down their concentration gradient from high to low concentration without energy, like a ball rolling downhill. No graph needed. It's just stuff moving to where there's less of it. In the GI tract, water moves passively from low Na+, less crowded, to high Na+, more crowded areas via osmosis across semi-permeable membranes. Your ball's on the right track, just rolling to the emptier spot. Clear? Want an example in the gut?
Yeah, and how does this differ from like against concentration gradient?
Down a concentration gradient, passive transport is when molecules move naturally from high concentration, crowded, to low, less crowded, no energy needed, like water flowing downhill. Against a concentration gradient, active transport is forcing molecules from low to high concentration, like pushing water uphill using energy, usually ATP. Example, in the GI tract, NAFI moves passively down its gradient into cells, high Na plus in lumen to low in cell. But NAFI K plus ATP ACE pumps NAFI out of cells against its gradient, low to high, using energy to maintain gradients for absorption. Clear? Want a gut specific case?
That makes sense actually. But yeah, explain to me one more time.
No worries. Let's make it stick. Concentration gradient is like a slope. High concentration, lots of stuff, like not an eddy, is the top. Low concentration, less stuff, is the bottom. Passive transport. Molecules slide down the slope. From high to low, no energy needed, like a ball rolling down a hill. Example, Water moves from watery gut, high water, to salty blood, low water, by osmosis. Active transport. Molecules are pushed up the slope, from low to high, needing energy, ATP. Example, natty pumped out of gut cells to blood, low to high natty, to keep absorption going. Passive, easy slide down. Active is hard push up. Clear? Want a simpler analogy?
So one is push up.
My bad. Push up was just an analogy. Against a concentration gradient, active transport means moving molecules from where there's less of them, low concentration, to where there's more, high concentration, like pushing a ball up a hill. It takes energy, usually ATP. Example, in the gut.
I see. Okay. So, with passive transport, cells are permeable to non-polar hydrophobic molecules and some small uncharged polar molecules, whereas non-permeable means that non-permeable. Yeah, explain this. I don't even know how to form the question, like regarding large and charged polar molecules and non-permeable to movement. Yeah.
Yo, I heard you talking another language, but I know it was wrong because you'd never do that. Sticking to English. Let's clear up passive transport and permeability. Passive transport. Molecules move down their concentration gradient, high to low, through cell membranes, no energy needed. Permeability depends on the molecule. Permeable, nonpolar, e.g. oxygen, CO2, and small uncharged polar molecules, e.g. water, urea, slip through easily via diffusion. Small size or fat solubility helps. Non-permeable, large polar molecules, e.g. glucose, and charged ions, e.g. natty, Cleopoly, can't cross freely. Membranes block them due to size or charge. They need channels or carriers. Facilitated diffusion, still passive. Example, in gut, water, small, polar, moves passively into cells. Natty, charged, needs a channel. Non-permeable molecules rely on active transport or special paths. Clear? Want an example with gut absorption?
I want to ask you about symport and antiport and secondary active transport, how it connects to sodium potassium ATPase. Yeah.
All right, let's break down simple transport, antiport, and secondary active transport tied to sodium potassium ATP. Simple transport, molecules move down their gradient, high to low via a single channel or carrier, no partner. Example, water via aquaporins and gut. Antiport. Antiport, two molecules move in opposite directions through a shared transporter. One down its gradient, one against. Example, natty, clia, dopa exchanger in cells. Sodium potassium ATPase pumps 3 natty out, 2 kPa into cells, using ATP, creating low natty inside, high natty outside, gradient. Secondary active transport uses the natty gradient from ATPase to drive another
I'm just
molecule
gonna
against its
interrupt
gradient.
you.
No direct
Hey.
ATP.
Hey.
Example.
Okay. I need to interrupt him, guys. Because he's saying natanabi. Or whatever the fuck. He means sodium and potassium and all that. Okay. I still don't get the, in a sentence or two, remember, the next 200 messages, I want you to be nice and direct, with the least amount of words to get your point across. But yeah, explain to me again secondary active transport. please. Krok.
Secondary active transport uses the sodium gradient from NASHA PS to move another molecule, like glucose, against its gradient without ATP. Example, NASL glucose import in gut pulls glucose in as NASL flows down its gradient. Clear? Want an analogy?
I don't get the difference between primary and secondary.
Primary active transport uses ATP directly to move molecules against their gradient, like NASI K plus ATPS, pumping NanoS out, K plus in. Secondary active transport uses the gradient from primary, like NanoS gradient, to move another molecule against its gradient. No ATP, like NanoPH, like NASL glucose import, like NanoPH, like NASL glucose import in gut. Clear?
No, so
Need an
one
example?
one uses directly ATP, excuse me, and the other one.
Yo, I heard you talking another language, but I know it was wrong because you'd never do that. In English, primary active transport uses ATP directly, e.g., NanoPH KATPS moves NanoS out, K plus in. Secondary active transport uses the NanoPH gradient from primary to move another molecule, like glucose no ATP, e.g., NanoPH KATPS. Example, NanoPH KATP. Example, glucose import. Clear? Want a quick example?
Yes. Give me an example, yes.
Primary, NanoPH KATPS uses ATP to pump 3 nanos out, 2K plus into gut cells, creating NanoPH gradient. Secondary, NanoPH glucose import uses that NanoPH gradient to pull glucose into cells against its gradient. No ATP. Clear? Want another?
Well, it's a bit confusing the way you talk. Let me check what it's actually saying, guys, because it's messing up the language, isn't it? So it's saying primary sodium potassium sodium potassium ATPase uses ATP to pump 3 sodium out, 2 potassium in. Secondary sodium glucose import uses that sodium gradient to pull glucose into cells against its gradient. No ATP. Okay. Alright, that makes sense. Okay. Let's talk a bit about principles of enterocyte transport.
Enterocyte transport moves nutrients, water, and electrolytes across gut cells, enterocytes into blood. Principles: passive transport. Water, small molecules move down gradients via diffusion, channels. Example: water. Only about 20% of gut mics are liposome and nitride, microgalactic nitroglycerin gels. Example: water via aquaporins. Facilitated diffusion. Glucose, amino acids use carriers down gradients. Example: SGLT1 for glucose, primary active transport, EPT, NTSK nitride, active transport, ATP, pumps nitride out, KSIN, setting gradients, secondary active transport, ESGL. Nitride gradient drives glucose amino acids against gradients, ESGL. nitride glucose symport. Osmosis. Nitride absorption creates hypertonic lumen, pulling water. Apical membrane. Lumen side takes in nutrients. Basolateral. Blood side releases to blood. Clear? Want a specific nutrients path?
Yes. And what does it mean that it's polarized with an apical and basolateral membrane?
Polarized means enterocytes have distinct sides for specific jobs. Apical membrane faces gut lumen, absorbs nutrients, electrolytes via transporters, ESGL. Nitride symport. Example, media post-apical, symport group. Basolateral membrane faces blood, releases absorbed substances into bloodstream via different transporters, ESGL. GL2 for glucose. Polarization ensures one-way flow, in from lumen, out to blood. Clear? Want a nutrient example?
I'm still none the wiser of that what that means. And I don't understand what tight junctions do. So they provide a barrier to free flow the gut lumen contents?
All right. Polarized means enterocytes have two specialized sides. Apical membrane, gut lumen side, grabs nutrients like glucose via transporters. Basolateral membrane, blood side, releases them to blood. Tight junctions are protein seals between enterocytes, blocking free flow of gut contents, like bacteria, toxins, between cells, ensuring controlled absorption through cell membranes only. They maintain the barrier and polarization. Clear? Want an example of a nutrient's path?
Sure.
Glucose transport. Apical membrane of enterocyte uses NTS glucose symport, SGLT1, to pull glucose from gut lumen, driven by nitride gradient, secondary active transport. Basolateral membrane releases glucose to blood via GL2, facilitated diffusion. Tight junctions seal cells, forcing glucose through enterocytes, not between them, ensuring controlled uptake. Clear?
Yes.
Want another
And we have transcellular and paracellular too. And solvent drag.
All right, let's track another nutrient, sodium, nitride. Transcellular, nitride enters enterocytes' apical membrane via nitride H plus exchanger or co-transporters, secondary active. Exits basolateral membrane to blood via NTSK INTTAC, primary active. Paracellular, some nitride slips between enterocytes through tight junctions, driven by electrochemical gradients. Solvent drag. Nitride and water absorption create a hypertonic lumen. Water flow, osmosis, drags nitride paracellularly. Tight junctions limit paracellular flow, favoring transcellular control. Clear? Want another nutrient or more on solvent drag?
Not so good. I want to understand the crypts and villi a bit. How they express different combinations of transport proteins. And the enterocyte on the SI villi are absorptive, but in the crypts they're secretory.
Villi and crypts in the small intestine, SI, have distinct roles. Villi, finger-like projections lined with absorption enterocytes, express transporters like SGLT1, nitride glucose, NTSK, INTT, exchanger for nutrient electrolyte uptake. Transcellular, maximize absorption via large surface area. Crypts, deep in
Yeah, go.
All right, picking up. Crypts house secretory enterocytes, expressing transporters like CFTR, chloride channel to secrete Cl, HCO3, and water into lumen, aiding digestion, fluid balance. Villi enterocytes absorb nutrients, ESG glucose via SGLT1, nitride via nitride H plus exchanger, transcellularly, some paracellularly via tight
How come
junctions.
though it's not the other way around, the secretory and the absorptive?
Villi are absorptive because their huge surface area, microvilli, and location lumen facing maximize contact with digested nutrients, expressing transporters like SGLT1 for glucose NTSK uptake. Crypts are secretory because they're deeper, less exposed to nutrients, and house stem cells plus enterocytes with CFTR channels, releasing Cl, HCO3, and water to lubricate lumen and aid digestion. It's evolutionary. Villi grab nutrients, crypts prep the gut environment. Clear?
Okay.
Want
Let's
more on
talk
their
a bit
protein
about
differences?
cobalamin and its absorption. So, yeah, there's quite a lot to say.
Yo, I heard you talking another language, but I know it was wrong because you'd never do that. Sticking to English. Cobalamin, vitamin B12, absorption complex process. In stomach, B12 binds haptocorin, saliva protein, protects from acid. In small intestine, pancreatic enzymes free B12. It binds intrinsic factor from stomach. Intrinsic factor B12 complex absorbed in ileum via cubulin receptors, carrier mediated. Low intrinsic factor causes pernicious anemia. Clear? Want more on issues or mechanism?
Well, I want to understand the intrinsic factor complex, the B12 haptocorin complex, how pepsin and HCl play a role. Tell us this in a form of a nice story.
Once upon a time, in the bustling city of Stomachville, vitamin B12 arrived via a meaty meal. To survive the acid swamps, HCl, B12 met haptocorin, a loyal guard from Saliva Town, forming the B12 haptocorin complex for protection. Pepsin, a local chopper, helped break food proteins to free B12 for this bond. The duo ventured to Duodenum Creek, where pancreatic enzymes, like knights, shattered the haptocorin shield. There, B12 met intrinsic factor, a wise guide from Stomachville's parietal cells, forming the B12 intrinsic factor complex. This pair sailed to Ilium Port, where cubulin receptors, like dock workers, pulled them into enterocyte homes for absorption into bloodstream river. Without intrinsic factor, B12 would be lost, causing pernicious anemia. And so, B12 lived happily in the body, aiding blood and nerves. Clear? Want more on absorption issues?
That's clear.